Alright, today we're going to start talking about Chapter 6. Specifically, we're going to focus on z-scores. So I want us to start with a comparison. Which is more impressive, a 55-yard field goal in the NFL or a 100 miles per hour fastball in the MLB? Now, it can be quite difficult to make a comparison between these two groups because they're very unique sets of data. How can I say that one is more impressive than the other when they're measuring completely different things? Now, we want to make these comparisons. We want to make these comparisons all the time. So what we want to do is somehow change this data to make them less unique. So what we're going to do is use standard deviation as our ruler. Whenever we have very different looking data, often using that standard deviation can help us kind of compare these different data points. So the standard deviation tells us how the whole collection of values vary, so it's a very natural ruler that we can use to compare an individual to a group. As the most common measure of variation, the standard deviation plays a very crucial role in how we look at our data. When we want to compare an individual data value to their mean in relation to the standard deviation, we're going to use the following formula. So it says z equals y minus y bar over s. I want to go through and just talk about what each of these variables mean in your formula. So this z here is representing your z-score. The y is your individual data point. Y bar, we've seen before, this is your mean, and S is your standard deviation. So what we're doing with this formula here is we're taking our data point that we're looking at, we're subtracting the mean, so we're figuring out how far our data is away from the mean, and then to get it into measures of standard deviation, we divide by the standard deviation for this data. The result that we have is called the z-score. We will be using these z-scores all the time for the rest of the semester. All right, when we're working with z-scores, it's important to note that these z-scores have no units. Okay, z-scores measure the distance of each data value from the mean in standard deviations. So z-scores are measures of standard deviation. They're not measures of units. So they don't use feet, miles per hour, inches, no units here. If you end up with a negative z-score, it tells you that the data value is below the mean, while a positive z-score tells you that the data is above the mean. Standardizing values have been converted from their original units to the standard statistical unit of standard deviations. Now that might sound complicated, but what we're saying here is that when I convert things from these random different units of measure into standard deviations and z-scores, I'm able to compare all different types of values, all different types of unique data in a way that is relative to their specific mean. So it makes these comparisons much easier when you have various different groups. All right, so I want to do an example here. It says a company's customer service hotline handles many calls relating to orders, refunds, and other issues. The records indicate that the mean length of a call is 4.4 minutes with a standard deviation of 2.3 minutes. Calculate a z-score for a call that lasted 6 minutes. So I know they're asking for a z-score, so I want to use my z-score formula. And I should be given most of this information here. I don't know what the z-score is, that's what I'm trying to find. The individual call that I'm looking at was the call that lasted 6 minutes, so my y value will be 6. They told me that the average call length was 4.4, and the standard deviation was 2.3. I can use my calculator from here. So 6 minus 4.4 divided by 2.3 gives me a z-score of 0.696. Okay, now what that means is that this call that lasted 6 minutes was about 0.7 standard deviations above average. When we take our data and we convert everything into z-scores, what we're doing is shifting this data. So you're shifting the data by subtracting the mean, and then you're rescaling by dividing by their specific standard deviation. Whenever we're changing it into z-scores, you don't change the shape of the distribution by changing the mean and the standard deviation. What's interesting is by standardizing into z-scores, you make the center have a mean of 0. So we're going to see this normal curve quite often. When I have this normal curve, my z-scores always have a mean right here in the middle at 0. Also, standardizing into z-scores changes the spread, and it makes the standard deviation 1. Now we're going to denote this standard deviation by just making a little mark here and labeling that standard deviation as 1 unit. All z-scores have the same mean of 0 and standard deviation of 1. It stays the same for every single z-score. Alright, so how do you know when a z-score is big? A z-score gives us an indication of how unusual or how typical a value is because it tells you how far away it is from the mean. I know that if I had a z-score that was really, really close to the mean, it'd be pretty average because it's sitting right there at average. In fact, if a data value is right at the mean, it'll have a z-score equal to 0. It'll be right there at the exact average. So again, I'm going to go back to that normal curve. My average is right here at 0. If my z-score is 0, I know that my data point was equal to the mean. If I have a z-score of 1, it means the data value is 1 standard deviation above the mean. So if I draw in my standard deviation right here of 1, and I drop this down, here would be 1 standard deviation above the mean. Okay, it works the same in the opposite direction, so a z-score of -1 would be right over here. That's 1 standard deviation below the average. Okay, so how far away does your z-score have to be from 0 to be considered interesting or to be considered unusual? There's really no universal standard, but we need to understand that the larger a z-score is, whether it's very, very negative or very, very positive, the more unusual it is. Typically, what we'll see is that most of our data points will fall within 3 standard deviations of the average. So if I have my mean right here at 0, here's 1 standard deviation, 2 standard deviations, and 3 standard deviations. Most of my data is falling below 3 standard deviations above the mean. And the same is true as I go in the opposite direction. So -1, -2, and -3. Typically, we look at this z-score of 3 and -3 to kind of give us an indication of how unusual things are. I know that if I have something with a z-score between -1 and 1, it's not that unusual. It's very close to the average. But if I have something with a z-score of 3, well, that's very far from the average. It's far above average, so I'd say that that is quite unusual. Alright, so here's Ethan. He's unsure of which score to put on his college applications. He took both the ACT and the SAT. On the ACT, he scored a 25. On the SAT, a 1200. The national average on the ACT is 20.8 with a standard deviation of 4.8, and the national average on the SAT is 1083 with a standard deviation of 160. Which score is more impressive to put on a college application? Now, the ACT and SAT are graded on far different scales, so just looking at it might be a little bit difficult to make a comparison. So what we're going to do is convert these both into z-scores so we can see how impressive they are in relation to their average, to their mean. So for the ACT, I'm going to calculate his z-score. Okay, Ethan's score on the ACT was a 25. The average was a 20.8. And the standard deviation was 4.8. Using my calculator, I find this z-score is 0.875. Now I can see because this is positive, his score was above average, which I already knew because he scored a 25 in comparison to 20.8, but it's a little bit less than one standard deviation above average. When I go to compare that to the SAT, I'll do the same thing and calculate his z-score. His score on the SAT was a 1200 minus the average was a 1093 over 160. And his z-score for the SAT is 0.73. So although he was above average again with the SAT, he's only 0.73 standard deviations above average. So which one is more impressive? His ACT is more impressive because it's farther away, farther above the average. Okay, our last example here says if the national average on the SAT is 1083 with a standard deviation of 160, what score is needed on the SAT in order to have a z-score of 2.6? So this time, if I think about my z-score formula, they give me the z-score of 2.6. That's what I want my z to be. I want to have a score that is 2.6 standard deviations away from the average. Do I know what score I'm looking for yet? No, that's what they're asking. What score is needed? So I'll be solving for my individual, my y. The average was the 1083, and the standard deviation is 160. As I solve for y, I would multiply each side by 160. So 160 times 2.6, 416. I add 1083. And I see I would need a 1499 on the SAT in order to be 2.6 standard deviations above average.